Hello, everyone. For this Super STEAM Saturday, we have Tiffany Fields, who is an astronomy instructor at WCC, and she is going to do a really, really cool presentation called Coloring Our Universe, and I'm going to turn it over to you.
Amazing. Thank you so much. I am excited to chat about this, and hopefully we will learn a cool space fact or two and learn about how these beautiful space images that we typically see are created. So my plan is I'm going to do a little bit of an introduction. We'll go through some cool astronomy photos and learn about how they're made. So as I get into this here, will introduce myself a little bit too. So my name is Tiffany Fields. Like we mentioned, I am an astronomy instructor at Washtenaw Community College, but I'm actually joining today from Nova Scotia, Canada. And so you can see that on the map highlighted in the pink way off on the eastern coast. So I am not in the Ann Arbor area, but magic of Zoom, being able to share this all with us. So I'm joining from Nova Scotia, Canada. I teach online astronomy classes at Washtenaw Community College, and I also run an observatory with a big telescope here in Canada. So I have a lot of experience looking through telescopes and helping other people look through telescopes. And I hope that we'll get to learn more about the types of images that telescopes can take. I also want to point out, because I am sitting in my house here in Nova Scotia, I have not just two, but three dogs. One of them, this most recent photo, is a tiny puppy who is upstairs, and I'm hoping that he takes his nap during this whole session. So I hope that we don't get many puppy barks throughout. But these are my dogs. I love to introduce them. Hopefully you enjoy seeing them too. So let's get started a little bit here. So this is a picture of me using a big telescope here where I'm sitting, so in Nova Scotia, at the Burt Gaffney Observatory. So when I talk about observatories, whether they are in space or on the ground, they are places with big telescopes. And we can use big telescopes to look out into the nighttime sky to see what is out in the universe around us. Around Ann Arbor, there is the Detroit Observatory, and they offer free viewings and sessions and tours. So I hope that you get to check out their calendar and maybe go visit the Detroit Observatory. It looks so neat. So sort of getting into it here, when we look at images from telescopes, whether they're in textbooks or books that we get at the library or online, they're often these beautiful images. They're full of color, and I think that they're full of wonder as well. And these beautiful, colorful images that we get, like the one that we've got on the screen here, it's a combination really of science and art to produce this image. So we are going to sort of figure out how this is done and learn maybe a little bit about these images here. So my plan today, we will introduce astronomy and telescopes. We'll look at the electromagnetic spectrum because there's a lot of different types of light. We will look into some black and white images and see how they can be combined into color. And then I'll introduce an activity that you can do yourself online, and we'll sort of wrap up everything that we've done here. So we'll get started here. Astronomy, there is just so much out in the sky that we can see with our eyes and with telescopes, and so much that we can learn. Even this image that's in the background of the screen here, I think is just incredible. There is so much happening just in this one image behind the words astronomy. So this image actually, I'm just going to talk about it a tiny, tiny bit because I think it's so neat. Almost every point of light that we see in this image, all of those like oranges and whites, almost all of those are entire galaxies. So we live in the Milky Way galaxy, which is home to billions of stars like our sun. And almost every point of light in that one image there is also a galaxy with billions of stars. So there is just so much out in the universe that we can learn about. And I'm not sure if you can hear it, and hopefully you can't. Puppy has started barking upstairs, but we're gonna continue on. So thinking about astronomy, it might be useful if we define this, right? So that we're all on the same page. So astronomy is the branch of science that deals with celestial objects, space, and the universe as a whole. So if you want to study things that are outside of the Earth, out in our solar system, in the universe in general, that would be astronomy. And there is a lot that we learn in astronomy that helps us learn more about our own Earth as well. So let's take a little bit of a walk through the different types of objects that we might be able to see in the universe. So I'm just going to show some photos here, chat about them briefly. So this first one is an image of one of the planets in our solar system. So this is the planet Jupiter, and actually off to the side, there's a little dot there. It is actually one of its moons called Europa. And we here on Earth have one moon. We just call it the moon. But other planets in our solar system have so many more moons. Mars, for example, has 2 moons. Saturn and Jupiter have 60, 70, 80 moons. I can't keep track of the number of moons that Jupiter has. There was just announced that astronomers had discovered something like 12 or 15 new moons of Jupiter. So lots and lots of moons from these large planets out in our solar system. So this image, this beautiful color image, shows Jupiter and its moon Europa right next to it. And then we have other objects that are more like clouds of gas and dust out in the universe called nebula. So this is an image of the Stingray Nebula, and I think that this is particularly interesting because I've got 2 images side by side, right? One of them says 1996 at the bottom, the other one says 2016, and you can actually see how it sort of changed shape and color over those 20 years. So what we observe out in space is not only often colorful and huge and sort of weird looking, but it can be dynamic. It can be changing over time as well. And then here's a beautiful image, I think just stunning. This is a globular cluster. So a globular cluster is a type of object out in space that is a cluster of hundreds of thousands of stars, all sort of squished together in something that's like a bowling ball shape, but huge. And so something that is also particularly incredible is that there are black holes, hundreds and hundreds of black holes in this image that would be sort of in the center of this cluster of stars. And of course, we can't see black holes because nothing and not even light can escape them, but we can see their effects on the stuff around them. So that's how astronomers were able to figure out that there are a whole bunch of black holes in this particular image. And then moving on, I showed this image actually in a slide or 2 ago, and this is an image of a spiral galaxy. It's called M61, not a very fancy name, but this spiral galaxy is sort of like our own Milky Way galaxy, because our Milky Way galaxy is a big spiral galaxy as well, with billions and billions of stars. So this beautiful spiral galaxy, you can sort of see those arms coming out from the center, would have lots of stars, lots of planets around those stars, probably lots of nebula like the Stingray Nebula in that image, and probably globular clusters with black holes in them too. So when we're looking at a spiral galaxy or another galaxy like our own Milky Way, we can think about how similar it might be to what we're experiencing here too. And of course, all of these are beautiful color images with different like purples and pinks and blues and oranges all throughout. So the field of astronomy really is full of these just beautiful, colorful photos. But I think it's interesting to sort of step back and think about, how do we get these beautiful color photos? There's quite a few steps that go into it. So when we look up at the nighttime sky, maybe with just our eyes, we are able to see stars, maybe planets. We can often see the moon when it's up in the sky. But our eyes are, of course, limited because we can't really zoom in with our eyes. And we also can't like stare at one thing, one point in space, and then suddenly see a whole bunch of color out of it. So with like cameras, even our like cell phone cameras, you can take a long exposure image and say, open up that shutter to let the light in for 10, 30 seconds. But our eyeballs are limited because we can't do that with our eyeballs, which is probably a good thing. That would be very weird. But we can use things like telescopes to help bring those distant objects closer to us and to see more of those distant objects. So for example, tonight, the moon is up in the sky. We're just past the first quarter moon. If it's clear where you are, so this is of course for tonight, when I'm talking about this. And if others happen to be watching a recording later on, I recommend that you go see what phase of the moon it is, go see if you can see the moon in the nighttime sky. But tonight, this is what the moon would look like through a telescope if we would zoom in on it. And I totally recommend go try to find the moon in the sky. It is my favorite thing to look at. So we can use a telescope to bring those more distant objects and the light from those more distant objects to us to see them better. And there are different types of telescopes, but the way that I like to think about telescopes in general is that they are like big buckets of light. So the larger the telescope, the more light we can collect from dim objects out in the universe. So the larger the telescope, the better we can see those distant and dim objects. And so there are two main types of telescopes that I'll mention here. Some telescopes have lenses, like our eyes have lenses. So they would be like a piece of glass that bends the light to bring it to a focus. And when we bend the light and bring it to a focus all in one spot, we sort of gather all of that light together so that our eyeballs or our cameras can see all of that light really, really well. So lenses can bend the light so that we can see it better, or telescopes can have mirrors, sort of like a mirror that you might have in your bathroom to watch yourself brush your teeth. The mirrors in telescopes are usually slightly curved, just a little bit, so that the light can bounce off the mirror and then bring itself to a focus at one particular spot. So all of the rays of light would come together so that we could take a picture of it or look at it with our eyeballs. And so the way that this generally works, I've got different sorts of telescopes on the screen here, but the light would come in from the distant universe. And for a big telescope like this one, the light would hit the mirror that's at the bottom and bounce back up. And this big telescope actually has a second mirror at the top. So it just bounces again, all the way through to the bottom where all the light gathers into one small area to the focus, where we would put our eyeballs to look through the telescope, or we would put a camera to capture that light from the telescope. And so I'm sort of also going to focus on not only just using our eyeballs for astronomy and viewing the universe, but thinking about using cameras. So a camera maybe like you have in your phone, or a camera that you might just point and shoot. And considering too that there are really big fancy cameras that some big telescopes have on them too, but they work in a similar way where they collect the light that has come in and store it in like a digital file that you could open on your computer. So pointing out a couple of different telescopes that we might have heard of before. So on the left is the Hubble Space Telescope, and on the right is the James Webb Space Telescope. And I just mentioned that a telescope acts like a big bucket of light. And the larger the telescope, the larger the bucket, the more light we can collect from dim objects out in the universe. So something that I'm emphasizing here is the size of the mirrors of these telescopes. So I'm going to go forward one slide to zoom in on those mirrors. So the mirror is like the bucket that collects the light. And we can see how big the mirror is in the Hubble Space Telescope and in the James Webb Space Telescope. So for the Hubble Space Telescope and for the James Webb Space Telescope, there's a little person standing in front of those mirrors to give us a sense of the size. And so with these huge mirrors, we can detect light from very, very dim and very, very distant objects. The Hubble Space Telescope is one that you've probably heard of if you've heard of either of these. Hubble has been out in space for just over 30 years now, which is incredible, taking images of a whole bunch of stuff. And most of the images that we see in books or online are often from the Hubble Space Telescope. And then the James Webb Space Telescope, the one with that gold colored mirror, was launched very recently. So it's only been out in space for about a year and a half now, only been taking images for about a year. It is huge. So you can see that tiny person standing next to it. The mirror size is 6.5 meters, or like 18 feet in diameter. Like I'm trying to show that with my hands and my camera, and you can't because it's just so huge. And the James Webb Space Telescope is really, really special to astronomers and many other people because it's enabled us to see things out in the universe that we couldn't have seen otherwise yet. So the Hubble Space Telescope and the James Webb Space Telescope are working together out in space to take incredible images. And we'll get to how those can be taken. So we can use both our eyes and telescopes to do astronomy. And I want to emphasize that we often use telescopes to take photos of those objects in space. When astronomers are doing science on an object out in space, they have to take photos of what they're looking at to be able to analyze that data in a variety of ways. So we often use telescopes to take photos of objects out in space. But we have to take a few steps back here. Because when we are thinking about taking pictures of objects in space, we need to think about color and how we see color in general. So what I have in front of us is an image of the electromagnetic spectrum. This is just all of the different types of light that exist in the universe. And down the middle, there is a band called visible light. And that's the light that our eyes can detect. And it's a pretty small part of that whole spectrum. So what our eyes can see is only a little bit of all of the different types of light that exist. So the full electromagnetic spectrum ranges from radio waves to gamma waves. The wavelength of light for those goes from very long, many meters, many feet, to very, very short, less than the size of an atom. And as mentioned, the part that we see with our eyes is like really small. So there's a whole bunch of light out there in the universe that our eyes can't even pick up. So when we start to think about taking pictures in different colors, we can take pictures in colors other than what our eyes can see. And I'll illustrate that here. The Hubble Space Telescope that we were just talking about, that has been in space for 30 years, can see the colors that our eyes can see, so it covers the visible light there, but it also sees a little bit further, both in the reds and in the violets than our eyes can see. So it can see into the infrared and into the ultraviolet in that like pink shaded region there. That's what the Hubble Space Telescope can see. And if we think about the James Webb Space Telescope, it sees light that our eyes cannot even see at all. It's built entirely to look at infrared light, or light that is more red than the red that our eyes can see. So this is interesting, right? So the Hubble Space Telescope can see what our eyes can see, but it also can see more. And the James Webb Space Telescope in the yellow shaded region sees light that our eyes can't even see. And so the James Webb Space Telescope has given us a whole bunch of images of stuff out in space, but it's not been in colors that our eyes can see. So we have to sort of think about how color photographs can even be made of those things. I want to point out that there are so many different observatories and telescopes taking photos in all of the different wavelengths. So there are telescopes taking photos in gamma rays. There are telescopes taking photos in microwave or radio waves. Some of those telescopes are on the ground. Like in this image, you can see the Gemini Observatory. It takes images in sort of visible infrared light. And that one's on the ground. There are some radio telescopes that look like big television and discs. So like on the ground, the one that says VLA stands for Very Large Array. And it's just a whole bunch of essentially radio telescopes, which are just huge discs on the ground. And then up in space, there's a variety of telescopes. So for example, the one that's called NuSTAR or Chandra observe in X-rays. So thinking about an X-ray that you might get to see your bones, those telescopes are out in space observing those X-rays from distant objects in the universe. And there's Hubble on there too, above the visible light that our eyes can see, like we mentioned earlier too. And so I don't think that the James Webb Space Telescope isn't on this image, but it would be sort of where Herschel or Spitzer or Planck is in this diagram. So we as astronomers and we as engineers and scientists can create telescopes with certain mirrors, with certain properties to observe a specific type of light. Some of them observe the same stuff that our eyes see. Some of them observe things that our eyes cannot see, but we can create them to observe a very, very specific type of light. So there's this entire spectrum of light, and both our eyes and all of those individual telescopes only see parts of that whole spectrum at a time. So our eyes are limited to just part of a spectrum, and each of those individual telescopes is limited to just parts of the spectrum. So when we use telescopes with cameras to take images, they only see a small part of that full electromagnetic spectrum. And we as astronomers and scientists and engineers, we know what specific part of that light or what specific wavelengths that telescope and camera can see. Because we are the ones that built it, we know what it can see. So what happens when a telescope takes an image using a camera? It comes back as just a black and white photo. So all of those beautiful color images that we get in astronomy, they start out as just black and white photos like this one. And what's happening here is we could add color later if we wanted to. So this is a black and white or monochromatic image of a galaxy that I took using the observatory that I work with here in Canada. So this is just an image of a galaxy, and I know what my telescope can see and what my camera can see, so the image just comes back in black and white. And this particular black and white image, or all of the black and white images that we get from a variety of telescopes, what they do is they tell us how much light hit every single part of the camera. So the different parts of a camera sensor are called pixels, and we might have heard that word before. Maybe your camera has a certain megapixel number, and that tells you how many pixels are in your camera's sensor. So it sort of gives us the resolution of that camera sensor, how much detail or how fine detail it can see. And what's happening in this black and white image is every single pixel might get hit by some light. And the more light that pixel gets hit by, the more light will just sort of gather in that one particular pixel. And so if a whole bunch of light has gathered in one section of the image, like in the center of this spiral galaxy here, it is brighter than the rest. If more light gathers in just one or a few pixels, it will get brighter and brighter than the area around it. And so this is really, really helpful to us astronomers because it just tells us where the brightness from the distant universe ends up in our image. And because we as astronomers know what specific part of the light we are looking at, all we care about is how bright this object is in this specific section of light. So this is data that astronomers can use to learn more about these distant objects or distant galaxies out in the universe. But let's talk about then how we get those color images, right? So this is how the science and art combination starts to happen. So what we do to turn those black and white images into color, we take multiple images in a variety of filters. So filters that we put in front of a camera are sort of like sunglasses that we would put on our eyes. Maybe you have sunglasses that are red and some sunglasses that are blue. And when you put those sunglasses on, the world actually looks a little bit different because now you're only letting in red light or you're only letting in blue light. And what we can do with telescopes and cameras is specify what color of light we would like the detector or the camera to let in. So if I put a green filter on my camera, and then put a blue filter on my camera, and then put a red filter on my camera and take an image with each, I could get something that looked like these three images on the screen. So if I put the color red on the red image, the color green on the green image, and the color blue on the blue image, I can then add them together. And this can be done in programs like Photoshop, which I know is kind of expensive. There's a free program called GIMP or GIMP that does pretty much all the same things that Photoshop does, where you can assign colors to specific black and white images. And then what we do is just add them all together. If I, in one of those photo editing programs, told the program to add them all together, to put them one on top of the other, this is the image that I would get. So I get this beautiful colored image with some purples and whites and blues from those three individual black and white images. So there's a whole bunch of artistic decisions that could be made here, right? If I wanted my image to be more red, I could make the blue and green images be a little bit less saturated, be a little bit duller. So there's a whole bunch of artistic direction that this could take. And I'm going to show us another example. So this is another object. This is that spiral galaxy that we were looking at earlier. I took one image in a red filter, one with green and one with blue. And if we put those colors on those images and add them together, we can get this color image. And I think something really interesting is shown in this image here. If I go one slide back, we notice that there is a satellite passing through the green image. That's what that bright line is in the green image. It was a satellite in the sky that just sort of zoomed through the sky while the telescope was taking an image. It's just happening to be in the way when we were trying to take this image. And when we add them all together, that satellite line looks green because it showed up in that green image that I took. So I think that's pretty interesting here, how even when we're just looking at a galaxy, there are interesting things that we might pick up along the way. I also want to point out, this is how every single big telescope takes images and gets their color images. So this is sort of a three-step process that was shared from the James Webb Space Telescope. So that big gold-colored telescope that's out in space, on the left side, it's like almost entirely dark. It looks like maybe like if you rub your screen, it almost looks like there's just dust on there or something. But that is actually what the image looks like as soon as it comes from the telescope and into the computers of the scientists working with the James Webb Space Telescope. It almost looks entirely black. So what happens with those images is that they have to be stretched in a variety of ways. They need to be manipulated by the scientists and the artists that work with the James Webb Space Telescope. So they can take that almost fully black image and sort of stretch the colors in different ways to get the one in the middle, that black and white image in the middle where we can see all of that detail. And then after combining a bunch of different colors together, we can get a color image like the one on the right. So that would have been probably 10 or 15 different individual images, all with slightly different wavelengths of light that they were taking, that the telescope took an image of, all set to different colors, like I did that red, green, blue for the other images, and then combined together to get this beautiful image where the background looks blue and the foreground dust looks orange and brown. So this object is called the Pillars of Creation, and I actually think it looks sort of like a finger or like a hand reaching out into the universe. And I just want to, because this particular image is just so stunning to me, I want to point out what's going on in this image too. So I'm looking at the one on the right with the different colors. The oranges at the top of those little finger-like pillars would be newly formed stars. So in clouds of gas and dust, like these that we're seeing here, these nebulae, this is where stars are being formed in our galaxy and in the universe. So it's when a whole bunch of gas and dust sort of piles on top of each other. And when a little bit piles together, it's almost like you're making the biggest snowman that you possibly can. You just want to put more and more and more and more snow all on top of each other until you get this like huge snowman base. And that's sort of what's happening when stars are formed. A little bit of gas and dust clumps together, and then more gas and dust continues to clump on top of it until it becomes big enough to be a star. So there are clumps of gas and dust in newly formed stars, sort of at the end of all of these different pillars that we can see. And then in the background, there's just a whole bunch of stars amongst the blue background there. And so to say all of this, even the huge telescopes like the James Webb Space Telescope use that same process where we take images in a whole bunch of filters or a whole bunch of different wavelengths of light and combine them together to get a color image. And so this is an example where we see just 6 different individual images were all assigned a color and then combined together to create this sort of yellow and blue image on the right side. So there's a whole bunch of, I really want to emphasize, there's just so much artistic direction that could be taken here. All of the space images that we see don't have to end up looking exactly like they do. All of them are still representing what is actually out there, but we can observe them and we can visualize them in a variety of ways. So I think this is really beautiful. Just a really cool example of how images of the same object could look different if we chose slightly different colors or we stretched it a slightly different way than previously. This is another example from the James Webb Space Telescope. So this is an object called the Tarantula Nebula, sort of a spooky name as we're getting into the Halloween season. But this is the Tarantula Nebula, and up on the top there are 4 different images, a red, blue, green, and then one that looks like sort of black and sort of red. And all of these too are in different wavelengths of light. When we combine them all together, we can get that beautiful color image that we see there. And really, this all seems like something really special with just astronomy telescopes, but it's really how pretty much every camera works, like our cell phone cameras, except our phones do pretty much all of this work automatically in the background for us. If we look at camera sensors, there's typically a red, green, and blue sort of like portion of the sensor that collect light in, and then it all gets combined so that we can get a beautiful color image out. So when we are using telescopes and cameras and taking photos of things out in space, it's almost like we are deciding to do this step manually ourselves, which I think allows for really interesting outcomes. And of course, we can always take, our cell phone camera and put it up to the end of a telescope and it will take a color image for us. But there's more that can be learned if we specify, I want to take an image just in this filter, and then just in this filter, and then just in this other filter, and combine them together. And maybe I'll sort of emphasize that here. Telescopes, like I mentioned, can see things that our eyes can't based on the ways that they are created and the fact that our eyes can only see a small part of that full electromagnetic spectrum. So here is a particular object called the Crab Nebula that is out in space, and it's the remnant of a supernova. So this is the leftover gas and dust out in the universe after a star has exploded at the end of its life. And we see this same object in 5 different wavelengths on the screen here. And radio, we see it in radio, in infrared, in visible light, in ultraviolet light, and in X-ray light. And of course, the only ones that our eyes can see is the visible light. But we notice how this object looks different if we look at it in a different type of light. So when we observe something out in the universe, if we look at it in a slightly different type of light, we can actually learn something new about it. So what I could do here as an astronomer that might want to make a brilliant photo of this particular object, I might assign the color red to the radio. I might assign the color orange to the infrared, maybe green to the visible, blue to the ultraviolet, purple to the X-ray. And you could make different decisions of how you wanted to assign those colors if you'd like. This is just one example. And what could happen is we could combine all of those together to see what it looks like when you add all of those colors together. We would sort of get a better overall view of what this object looks like in all of the different wavelengths. But I'm not going to show you what that might look like. I will just leave it as a challenge for you because I'll show you how you can do this yourself. So at this point, there is a really cool website where you can try this on your own. So whether you're here in the call or if you're watching this later on in the recording, I hugely recommend that you go to this website from the National Radio Astronomy Observatory, the NRAO. where they have this really cool tool called Cosmic Coloring Compositor. And I'll show us sort of how it works, and I'll also share what that website looks like. So at this website, you can choose an object to start where you would want to combine a bunch of different wavelengths of light into a full color image. So you can choose an object to start, for example, the Crab Nebula, like we were just looking at, and we can turn on or off the desired wavelengths to add them to our image. So in this image, we have radio, infrared, visible, ultraviolet, and X-ray all available to us. We can then choose a color for each of those wavelengths. So all of them are just chosen as red right now, but you could pick those as any different color that you wanted. And you can adjust the brightness of each of those different wavelengths to bring out whichever details you think are most interesting. And then there is an option to save the image if you wanted to save it for like a computer desktop background or share it with your friends afterwards. And so I'm going to share just what this looks like in a web browser. So I'm pulling this up here. This is what it looks like, this Cosmic Coloring Compositor. So if I scroll down, I can click here on the Crab Nebula, and there's a whole bunch of different objects that I can try this out on. So maybe I'll pick M33, the Triangulum Galaxy. I have to click Select Image there. And it's loaded again with that particular object. And notice here, I've got 4 different wavelengths for this particular object: a radio, visible, radio 2, and visible 2. So it would have been looked at in 2 different radio wavelengths and 2 different visible wavelengths. Sounds great. And notice that I can pick a different color here. And this would look different on all of our computers, but this is just an example of how this might look. And maybe I'll choose a blue here. And maybe I want that blue to be really as intense as I can make it. Maybe I'll turn down that red a little bit, and you can start to see how we can create these images of our own. And this is just a start in all of the different ways that you can start to do your own astrophotography or astronomy image coloring. I want to point out too that most of the images and data from telescopes like the Hubble Space Telescope and the James Webb Space Telescope are freely available online if you would like to go and tinker with it yourself and see what sorts of images you can produce. It's available online. So I'm going to go back to my slide here. So I hope that you'll get an opportunity to try this for yourself, save those images, share those images. It would be really cool to see what everybody comes up with. And as a little bit of a treat, these are different ones that I sort of created. I think some of them look a little bit more weird than others. So we have the Crab Nebula M1 up on the upper left. In the middle, there's a spiral galaxy that looks pretty green, sort of bluish. And then the Milky Way center down on the right side looks particularly weird, but I love it. So just to fully wrap us up here, want to remind us that astronomy is the study of the universe in general, and we can do astronomy both with our eyes and with telescopes. And we've learned that telescopes take black and white images in specific wavelengths of light and then combine those images in specific wavelengths of light to create color photos. And there's a really cool animation that I found from the James Webb Space Telescope team where they start with a black and white image and it sort of fades into a color image. So as a reminder, my name is Tiffany Fields. I'm an astronomy instructor at WCC. My email is up there if you ever want to ask me some questions, or if you do this and create a brilliant color image and want to share, I would love to see it too. And at this point, if there are any questions from the folks that are here today, I would love to chat or just chat about anything you would like to chat about.